Hi! In this lecture you will learn the algorithm for finding fastest routes, which is used, for example, when you open your navigation app to get home from work faster, or by logistics companies when they want to deliver the goods to their customers in time but use less cars and less people. So let's first state the problem. It's really easy to do. For example, what is the fastest route to get home from work? Or more generally, what is the fastest route from point A to point B right now? And below you see a screenshot from a popular navigation app, Yandex Navigator, which is given a task of getting the fastest route from the point you are currently in, which is marked by a circle with the letter Y in it, to the finish, which is your destination. And it suggests you a few variants. So the default suggestion is the fastest route, but there are two others, and there may be, for example, a route which uses less turns, or the route which is easiest for a novice driver, and sometimes there can be a shorter route which is not the fastest one, but shortest one in terms of distance. So in this problem we can represent the city or the country as a graph where nodes are some positions in the country, for example the crossroads, and the edges are the roads that connect those crossroads, and there are some weights on those edges, and weight on an edge is in this case the time in seconds or in minutes you need to get from start of the edge to the end of the edge. And what you need to find is the shortest path in this graph, but not shortest path in the graph in terms of the number of edges, shortest path in terms of the sum of the weights of those edges. So if you want to get from A to B in the smallest amount of time possible, then you get by some path with some edges and some weights on those edges corresponding to the time, and you just sum up those weights of the edges and you get the total time it will take you to get from A to B. You want the fastest route, so you need the shortest path in terms of the sum of the weights of edges on this path. Let's see now, does the breadth first search algorithm from the previous lesson maybe help us. So let's look at this graph. Here we see that node A has a direct edge from A to the point B where you need to get. And so what our breadth first search would say us is that we already know the optimal path from A to B, because there is a direct edge, and so there is no point in getting to some other nodes. You just go directly from A to B, right? Well, this doesn't work. For example, in this case, let's suppose that it takes 5 hours to get from A to B, and the corresponding weight of the edge from A to B is 5. And let's suppose there is another node C, such that there is an edge from A to C, which takes 2 hours to go through it, and another edge from C to B, which also takes 2 hours to get through it. And of course this looks a little bit strange, but if there is a traffic jam on the road from A to B, and roads from A to C and from C to B are free roads where there is no traffic jam, then this can happen. And so then we see that going from A to B through C will take just 4 hours, while going directly from A to B takes 5 hours. And so our breadth first search algorithm doesn't work. So maybe it's vice versa. Maybe it's always better to work around, to go around some node, not to go directly. But that's not also not the case, because if the edge from A to B is 3 hours and edges from A to C and from C to B didn't change, and we just removed the traffic jam from A to B and it became 3 hours instead of 5, it is now better to go directly from A to B. So there is no universal rule to go directly or not to go directly. We need something more clever than that to solve our shortest or fastest route problem. Now let's gain some intuition about this problem. So let's look at this graph below and assume that we stay at origin node S, and we only know that the edge from S to B is going to take 3 hours, and from S to C is going to take 5 hours. So can we be sure that the distance from S to C is equal to 5, that it will take 5 hours for the optimal route from S to C? Okay. So no, this is not the case, because, for example, the edge from B to C can have weight 1, and so the shortest route from S to C will be from S to B and from B to C, which is only 4 hours instead of 5 hours if we go directly. So we cannot be sure that the shortest, the fastest route from S to C is 5 hours. Now another question is, can we be sure that the distance from S to B is equal to 3? And in this case, the answer is yes, because if we don't go directly from S to B, what other options do we have? We can go only from S to C and then go by some other edges to come to B. But if we go from S to C, we spend already 5 hours. And after that, we also spend some time to get to B. And that time is non-negative, so we cannot spend less than 3 hours time in the end. We actually cannot spend even less than 5 hours in the end. So going from S to B directly by 3 hours is beneficial for us. In terms of the graph and the weights of the edges in it, it means that there are no negative weights on the edges. All the weights are non-negative numbers, and so we cannot decrease the length of the path by going through them. So if we have already a path of length 3 and all other paths start from spending more time, we cannot improve this direct path. And in the next video we will use this idea to create a naive algorithm that solves our fastest route problem.